The big picture is that state machines give us a way of formalizing decision logic, discrete decision logic, sequential decision making, okay? And you can use it to formalize fairly complex behaviors. And in some ways, when you use state machines manually, they don't look very tractable, right? In some sense, the examples that we look at are all oversimplified. Okay, they don't really respect the realities of a situation, which tends to lead to complexities that are, can become overwhelming when you're using a bubble and arcs kind of diagram. We add some notation to the state machines that enables us to handle a little more complexity manually. For example, extended state machines, which give us the ability to manipulate variable values as part of the state machine, and concurrent composition of state machines, where we can take two relatively simple state machines and compose them either synchronously or asynchronously. The composition itself defines a state machine that can be quite a lot more complex than the two individual components, right? So that, as a general engineering principle, this is a good thing to do, right? You break down a complicated system into simple components, and you're not eliminating the complexity in the complicated system. You're just making it a little easier to understand, right? But the real value in state machines is that if you have a good formal state machine model, then it's subject to mechanized analysis, okay? And that's where the real value comes in, where I shouldn't say the real value. It's also valuable, for our limited brains to try to understand a system, right? I mean, just attempting to construct a state machine description of some system can give you a lot of insight into that system. So it is valuable for the human cognition part. But it's even more valuable because you can throw automated tools at these state machines and they can reveal behaviors that you didn't expect, and you can use them, for example, to check for safety conditions. So I'm going to try to illustrate that today. And again, I'm going to have to oversimplify the state machines in order to do it manually, but hopefully it'll give you a sense of how you can use them with an automated analysis. Okay, so just as a reminder, we talked about synchronous composition, and here's a very, very simple example. Two state machines with no inputs. So again, I want to remind you that one of the key principles in our state machine formalism is that the state machine itself doesn't decide when it reacts. Okay? The state machine says nothing about when it reacts. The environment chooses when the state machine reacts. Okay? When you have a composition of state machines, the environment chooses when the composition reacts. Okay? You then get to choose what it means for the composition to react. But the environment's going to choose when the composition reacts. So the environment chooses to react this composition of A and B. Okay? And the question is, what do you do? If you choose to do synchronous composition, then the two machines react simultaneously and instantaneously. Okay? And in doing so, they're actually behaving like another state machine, a single state machine, which is described over here. Okay, their simultaneous and instantaneous reactions will take you from the initial state, S1, S3, which is this initial state, to the next state, S2, S4, in one step, instantly. Okay? And you'll produce the output B. And then in the next reaction, when you're in state S2, S4, you will instantaneously go back to the initial state. Okay? So when you're doing composition of state machines, the first thing to do is to try to understand the state space of the composition. And a brute force way to get a state space for the composition is just form the product space. So each of these state machines has some number of states. In this case, these are not extended state machines, so the number of states matches the number of bubbles. Okay? But if it's an extended state machine, it doesn't. Right? But in any case, each state machine has some number of states. if you have two state machines, this one has some number of states, this one has some number of states, then the total possible state space for the composition machine is the product of those two state spaces. Okay, so in this case, 2 states here and 2 states here gives us 4 states there. This, by the way, just forming the product space tells you why this is actually a powerful methodology, because you can describe complex systems with lots of possible states using state machines that don't have very many states, right? And that's where the engineering value comes in being able to modularize systems, right? But, okay, so in this case, the product space has 4 states, but 2 of those states are not reachable. There's no path to them from the initial state, okay? So are they in the state space? Well, sort of, but not really. And in fact, we're going to look later at the notion of equivalence of state machines, okay? What I do have described here is a 4-state state machine. It just happens that 2 of the states are not reachable. But this state machine is equivalent in a very strong sense to a 2-state state machine that doesn't include these states, okay? That notion of equivalence we can formalize as well, and we will, in fact, formalize it. And it's very useful to formalize that notion of equivalence because you can determine if you simplify a system, have you changed its behavior? Okay? That's an important question to ask. Okay. All right, so that's synchronous composition. If we take the same 2 state machines and we compose them using asynchronous composition, then we have some choices because the phrase asynchronous composition by itself isn't enough to tell us what it means for the 2 machines to react. If I choose an interleaving semantics for my asynchronous composition, then a reaction of the composition consists of first non-deterministically choosing one of the 2 machines and letting that machine react. Okay? And then in the next reaction, I non-deterministically choose one of the 2 machines and let it react. Okay? That's what an interleaving semantics for asynchronous composition means. And the resulting composition is itself a state machine, which again has 4 states, but in this case they're all reachable. Okay? And the resulting composition is a non-deterministic machine. There's more than one possible reaction in each state. All right? Now, okay, so let's see if we can apply this composition mechanism to a real problem in embedded software. Okay? So you remember we looked at this piece of code when we were talking about interrupt service routines and how to control timing in a program. And the idea is that, I want to write a program that's going to do something for 2 seconds and then do something else. Okay? So this might be, some initialization phase. It's your program is supposed to make pleasant sounds for 2 seconds so that everyone thinks that they're happy, and then it goes on and does whatever annoying things it does after that. Right? Whatever it is. Okay, you're going to do something for 2 seconds and then go on. So the question is this code correct? All right. Now, one way to pose the correctness question is, do you in fact get to the point in the code after this 2-second loop? Okay, can you assure that you will get there? That would be one simple correctness criterion, right? I'm not even going to worry about whether it takes 2 seconds. Just will I get there? Okay, that's if I can show that there's a way that I won't get there, then I clearly have identified a bug in the program, regardless of the timing. Okay. All right. So can we use state machines to analyze this problem? That would be the key question. All right. So, of course, this is a C program, and according to the von Neumann model of computation, a C program executes as a state machine, right? And under the von Neumann model, your computer starts with an initial state, which is the contents of the memory, okay? And then your instruction set architecture has a set of operations that transform the memory. Memory here includes the registers and everything, all the possible state of your machine, all of the memory in the machine. Each instruction changes state. Now, the number of states is enormous, right? I mean, if you have 2 gigabytes of memory, 2 gigabytes is 16 gigabits, okay? So the state of the main memory in this machine has 2 to the a lot. There's a lot of states, okay? So you're not going to want to represent the state of this machine using a bubble and arc diagram, okay? It's not going to work. So we're going to have to abstract somehow what this program does, okay? So one way to abstract programs in a useful way is let's just look at flow control, okay? How does the execution proceed through a sequence of instructions in the program? So we can identify sort of key points in the program like this. So for example, I identify a position D just before a branch and a position E just after the branch, okay? Similarly, the while statement is also a branch. So I've got a position A just before I enter the while loop, a position B when I'm starting the body of the while loop, and a position C, which is what I'm ultimately interested in is, will I get to C? Okay? That's going to be the question that I'm going to ask. Okay, so if I say these are all the interesting points in the program, then, can I answer this question definitively using state machines? So I want to emphasize the word formal again here, okay? Because the informal way to do this is you kind of scratch your head, you look at this program, you think through all the possible threads of execution that you can come up with, and you kind of form an understanding of how the program works, and you come to a conclusion. And the problem is that with non-trivial systems, this is a pretty trivial system, so you can probably go through all the possibilities, although there's a pretty good chance even with this you're going to miss some, okay? But with a more complicated system, I guarantee you will miss some, okay? You're assured of missing some. And so the formality of the mechanism means that we can actually do an exhaustive search. You can actually study all the possible executions kind of all at once. And that's the power of the method. Okay, so let's try to apply state machines to this model. So here are 2 state machines for the 2 parts. There's a main program and there's an interrupt service routine. And in good engineering practice, I want to modularize this program. I'm going to describe each of these 2 components using a state machine. Okay? And I could do it like this. There's many choices, by the way. I mean, there's kind of an art to constructing these models, although you can also mechanize the construction of these models, but the result of a mechanized analysis of this program will be a much bigger state machine, and it's not going to be one we're going to want to look at manually because it'll overwhelm you, right? It's one that you're going to want to look at automatically. But when you're constructing these things manually, you choose some abstractions, okay? So here's one possible choice. So the main program, let's just say, okay, nothing interesting happens until we get to A, so we'll just call that the initial state, okay? And it's an extended state machine where we have a timer count variable that we initialize to value 2,000 as we enter the initial state, okay? Then do we go to B? Well, we go to B if the timer count is non-zero, right? And after we're in B, what do? Well, we always return to A. Okay, that's the only thing B can do because this is a while loop. So after B, I just go back to A. All right? When I'm in A, if timer count is 0, I will go to C. Okay, so that's a nice state machine abstraction of a pretty simple snippet of code. Okay, let's look at the interrupt service routine. The interrupt, yes, question, Gil. Good question. So the question is, when does the move between B and A happen? Remember that in our state machine formalism, your state machine doesn't get to choose. Okay? So this is a key question that we're going to have to resolve, is when is this thing going to react, and how are we going to coordinate the reactions of these two state machines? Are we going to do synchronous composition, asynchronous composition, or something else, right? Okay, for just one state machine, in fact, the C program doesn't say either. Okay? The C program says nothing about when you go from the end of this while loop to do the test again. Okay? There's nothing in this model that says. It's a perfectly valid execution of this C program to enter this block of code and then put my machine in suspended animation and go out to lunch and come back and then start the clock up again and go back to while. Again, all the C program says is these are the sequences of operations to be performed. It doesn't say anything about when they should be performed. Yes? So our formalism has the same property as the C code, which is that the formalism says nothing about when that transition is taken. It just says that if you're in state B and the machine reacts, then it will go to A. Okay? Yes, question. No. So the question was, if we're in B and timer count reaches 0, will it go to C? And the answer is no. Certainly not in the formalism, because there's no transition there, but also not in the C code. Okay, so the model is a good model of the C code, because B is the state of the program execution, in fact, before I even enter this block of code. Okay? So once I've made the decision to enter the block of code, I'm at B. At that point, if timer count goes to 0, nothing happens. I will execute this body of code until I go back to doing this test again. Right? Does that make sense? Yeah. C doesn't work that way. There are programming languages that work that way. So in particular, if I wrote this program in strl, okay, I could say, while watching this timer count, execute this. And if the timer count goes to 0 during the execution of this, I could abort the execution of this and go to the next step. But that's not the way that's not the semantics of C. C is going to test this timer count only at the beginning of this while loop, and it ignores its value during the execution of this body of code. Right? At the end of the execution of this body of code, it goes back to the beginning and performs the test. Again. Okay? Which is exactly what our model says. At the end of the execution of that body of code, we go back to the beginning and perform the test again.
So A of 0 is actually the time between your time function set and before B starts executing.
Yeah, so one of the problems is that, what exactly do I mean when I put these arrows here saying this is where we are in the code, okay? And because it can be a little bit tricky. But what A means is I'm about to do the test, okay, to determine whether to take the branch to execute the body of code or to skip to the next execution, right? That's what A means, okay? And then B is I've already made the decision, and I'm now going to execute this body of code, okay? Yes?
I was previously said that in the body of the loop code, you could pause the program indefinitely.
Yep. Right. Yes, that could happen. Yeah. So if you were to pause the execution of this body of code indefinitely, your timer interrupt could still kick in. This model doesn't. This lower state machine by itself doesn't say anything about what happens. Okay, because so far it doesn't include the interrupt service routine. But in fact, the C program also doesn't really say what happens. Okay? It's a perfectly valid execution of the C program to pause this indefinitely and let the interrupt service routines continue to execute. That is a valid execution, yes.
Question on notation.
Yeah. Mm-hmm.
When we want to denote that we're going from a state to another state on the next clock cycle, on the next event, don't we also use an arrow transition without anything written on it?
So, whoops.
Like for example, if you want to go from B to C on the next clock cycle, how can you denote that within our state machine? Like on the next
no.
event, and the event is a clock, yes, it's synchronous.
Yeah. So in our formalism, the transitions only describe what we do in a reaction when we're in this state. Okay? There's actually, the notation does not directly provide any way to say, if I'm in this state, then not in the current reaction, but in some future reaction, I'd like to go to C. All right? The only way we have to say that is to go to an intermediate state.
No. My question was between any two states. I thought like in synchronous state machines, if you have a transition without anything written on it, it implies on the next event, which is the clock cycle.
Well, yes, that's right. So the transition from B to A has no guard on it. And in our notation, that's just a shorthand for the guard is a Boolean that evaluates to true always.
Yeah.
So this transition will trigger. If you're in state B and the machine reacts, we will move from B to A. There's no question. There's nothing to test. Okay? Okay, these are good questions because, I mean, there's a lot of arbitrariness in this notation, but there's a lot of arbitrariness in any formal notation. And so in order to use a notation, you have to get used to it, right? And you can't argue that it's wrong unless it's inconsistent with itself, right? All formal notations that are consistent are equally correct. Formal means devoid of meaning. The most useful formal notations are not only correct, but also useful, right? And hopefully this one is both correct and useful, but, there are arbitrary decisions, and you sort of have to get used to it in order to use it. Okay? Okay, so we've got, I think, hopefully everyone's on the same page and understands this first state machine pretty completely. Yeah. Mark?
So A with a self would also be a faithful representation, right? Just if the timer count equals not 0, self loop to A, you can just discard B. There's no option.
Yeah, actually, that's a good question. So if A had a self loop, would this still be a faithful notation? In fact, because of the semantics of C, I could put a non-deterministic self loop on all of these states, and it would still be an accurate description of the C program. Oh, I see what you're saying. Yeah, this is another shorthand in our notation, right? Which is, if we're in state A and well, actually we have all the conditions covered, right? In this case, so. But you could have a state machine that's incomplete in the sense that you could be in a state and there's no enabled transition out of it, and we implicitly assume there's a self loop that is taken if no other transition is enabled.
So the question is, can we discard B desired? Would it still be faithful?
Oh.
And that the timer count equals not equals 0, loop to A.
Oh, I see. And get rid of B altogether.
Yes.
Yeah. So Martin raises a very good question. I mean, would this state machine be equivalent if we just eliminated B and had, instead of this transition from A to B, it just went right back to A? And if you look at this state machine by itself, then yes, it'll be equivalent. But I'm not sure it's going to be equivalent when we compose it with the other state machines.
There must be some other state machine which we can synchronously compose and then...
Right. Yeah, so I'm glad you raised that question because I'm going to put that on the second midterm. Because at that point, you will have the equivalence refinement ability to compare state machines and determine under what circumstances they are exactly equivalent. And this would make a potentially very nice example for testing that mechanism. I'm not sure what the answer is, by the way. So it will depend on how we compose it. Yeah.
So in the ISR, when you disable interrupts and then enable interrupts, I just have a question about timing.
Yeah.
When you disable it, that'll stop the timer interrupt from running, right? But then when you enable it, will that reset with a new millisecond? Or because I'm thinking if you disable and then enable, the time that it takes to decrement timer counter will add to your running time of your program. So you wouldn't be exactly 2 seconds. You would have that added time.
Okay, so that's you raise a good question, and it's a slightly complicated question because really it deals with what really does it mean to disable interrupts here, and then re-enable interrupts. Okay, and I'll tell you what it means from the perspective of this C program model, and it's actually quite simple from the perspective of the C program model, but how it manifests in a physical system is not so simple. From the perspective of the C program model, it simply means that this procedure will never be re-entered. So you don't have to write it to be re-entrant. In other words, if I'm executing this procedure, then I cannot begin a new execution of this same procedure until I'm done executing this procedure. Okay? That's the only thing it means from the perspective of the C model. Now, how that plays out in terms of timing is actually not expressed in this C program at all. And how it plays out in terms of timing is going to depend on the hardware that you connect up to this thing. What does the timer do? How does it handle toggling of the interrupt request line? What if the interrupt request line transitions during the time that I'm executing this interrupt service routine? Will it respond to the interrupt after it's done when it enables interrupts or not? That's up to the hardware, okay? And it's actually not expressed in this C program. This is, by the way, one of the real challenges with embedded systems is that actually we work with models that are very incomplete. They actually don't tell us a lot of things we need to know about how the system's going to behave. I consider this a flaw in our current technology, and it's valid to look at this critically and say, gosh, actually it would be nice to know that, and it should be expressed in the model, but it's not. Okay? All right. Okay, so first question. Okay, wait, let's make sure we understand the top state machine. Okay, so first of all, the interrupt service routine is a little bit stranger than main because in the main program I could clearly define an initial state being at position A. But the interrupt service routine, I can't really do that because when this thing starts up, it may not even, the interrupt service routine, I may not be anywhere. I'm not at D, I'm not at E, okay? Because the interrupt hasn't been triggered. So I needed to add an extra state, an idle state, which just says, I'm not in the interrupt service routine at all, okay? And now I need to define an external input, a cert, which is a pure input, okay, that will take me to D. Okay, so whenever that external input is provided, this interrupt service routine will go to D. And then when it's in D, it will test the timer count. And if the timer count is non-zero, it'll go to E. Okay? Otherwise, it will transition back to idle and issue an output return. Okay? If it goes to E, then it will unconditionally, in the next reaction, decrement the timer count and issue the output return and return to the idle state. Okay? So everybody understand that state machine describing the ISR. Okay. So how should I compose these? Should these be composed as using synchronous composition? I see a couple of shaking heads. Why not, Martin?
Because they're not synchronous. Interrupt can happen any time.
Right. They're not synchronous, so it would be really weird, right? And it would actually be an incorrect model of the behavior, right? Because it would say, well, all right. So suppose my initial state would be idle, comma A, all right, and then when the composition reacts, both machines have to react simultaneously and instantaneously. So if I get an assert at the input, I will transition to D, and depending on the value of timer count, to either B or C. But that's not what the C program does, right? Okay. So is asynchronous composition the right thing to do here? And if so, which variant? Should I use an interleaving semantics or, well, probably based on the same argument, the same reason I wouldn't use synchronous composition says if I'm going to do asynchronous composition, probably it better be interleaving. I don't want these two machines to react simultaneously. Okay? So then the question becomes simpler. Will asynchronous interleaving semantics be the right way to compose these two state machines? Yes?
So I wonder is like it's not deterministic which one gets updated, right?
Say it again?
I thought earlier it's not deterministic which machine gets
Right.
So it's really not going to update the other one, like deterministic.
Yeah, good point. What's your name? Sean. Yeah, so Sean nailed it. He said, I mean, if I choose an interleaving semantics, interleaving asynchronous semantics, then I could have asserted the interrupt service routine in B and D, and then in the next reaction choose to continue executing my main program even though I'm still in the interrupt service routine. And that's not the way interrupts work, right? The main program isn't going to resume executing until the interrupt service routine returns. Okay? And in fact, if I just brute force and construct the state machine that describes the non-deterministic, the interleaving asynchronous composition of these two state machines, there it is. Okay? And this state machine has state transitions that won't occur in practice. So, for example, it shows that I could go from AD to BD. That's a transition that's allowed in this composition, but the C program won't do that. Okay? So we're kind of stuck. We got two nice, simple state machines, and all the composition mechanisms that we've come up with so far fail. I don't know how to compose these. Okay? So let's choose a new composition semantics, which is hierarchical state machines. Okay? Now, in order to do this, I'm going to have to come up with some description of how the interrupt controller works. Okay? So there's going to have to be some logic that governs how these two state machines interact with one another. I have to capture the fact that if the interrupt service routine starts executing, it'll execute to completion. Okay? And I could capture quite a bit more detail about the interrupt service routine. So I could start to answer questions by, what's your name? That Josh raised, right? Which is, well, what does it really mean to disable interrupts, right? So I could, for example, have hardware that if an assert occurs while I'm in actively processing an interrupt service routine, then I keep track of the fact that assert has occurred and then ensure to later handle it when that service routine returns, right? I could capture that behavior in a state machine. But the hardware, this is a description of the hardware. This is not a description of the C program. This is not a description even of an instruction set architecture. It's a description of a particular realization of the microprocessor and the timers, okay? So, so I could do that. But I'm going to use a simpler interrupt service routine because with that four-state interrupt handler, I end up with too many states on the PowerPoint diagram, and again, you're going to be better off doing mechanized analysis than human analysis. So I'll simplify still further. But before I do that, let me explain hierarchical state machines. Okay? So again, there's a lot of arbitrariness in this notation, and this style of hierarchical state machines was originally introduced by David Harel in 1987 in a formalism that he called state charts. And that formalism, it turned out, his original state charts paper, it turned out, was not really a formalism. There were a lot of ambiguities. And in fact, people went off and misinterpreted his paper and came up with many different implementations of state charts, all of which had different semantics. Okay? At one point, I read a paper that cataloged some 28 different variants of hierarchical state machine semantics that were actually used by people in various contexts, and they were all different. So if you want to do anything, you have to pick one. So I'm going to give you one, okay? And it is formal in the sense that it completely defines the behavior, and it's not subject to human interpretation. If I give you a state machine, its behavior and set of possible behaviors is fully defined, okay? All right, so what does it mean to have hierarchy? Well, first of all, we associate with a state potentially a refinement, okay? So in this case, I have a two-state state machine with two states A and B, okay? And B has a refinement which is itself a two-state state machine. And the way to interpret this is that if I'm in state B, I'm actually in either C or D, okay? But it can be either one. Not both, one or the other. So this is called, in Harel's notation, he called this an OR state. He called B an OR state because it's not really a state. It's a placeholder for being in one of several other states. Okay? All right, so that says, well, all right, so immediately, how big is the state space here? How many states does this state machine have? 3? Actually, it's either 3 or 4, depending on another subtlety in the semantics. Okay? So let me give you a hint on this, and then we'll come back to this, right? When I transition from B to A, I might remember where I was in C or D. And when I come back to B, I might pick up where I left off. So if I left B while in D, then if the next time I return to B, if I am still in D, then actually this state machine has 4 states. On the other hand, if every time I enter B, I go to C, then the state machine only has 3 states. Okay? So David Harel introduced that notion as well, and he talked about transitions being either history transitions or not history transitions. And history transitions actually give you a way of describing enormously complicated behaviors very compactly. Okay? But the number of states can get quite large. Okay. Now, we have to define what it means for this hierarchical machine to react. So a reaction, by definition, of a hierarchical state machine consists of first the refinement reacts, and then the top-level machine reacts. But these are, even though they're sequenced, they're occurring in the same reaction, so that you view these as being simultaneous. Simultaneous and instantaneous, but you still have to do one after the other. Seems almost like a contradiction, but from the external view, what this means is, for example, suppose that I'm in state B, and the machine reacts, and both guard G1 and G4 are both enabled. Okay? Then what's going to happen? Well, the refinement reacts first. I go from C to D and I produce output A4. And then the higher level state machine reacts and goes from B to A and produces output A1. And the important thing here is that A1 and A4 are simultaneously produced by this state machine. Okay? They are both present on the output in this one reaction. All right? Okay, so this is a possible sequence of reactions. This is a trace, which is a way to keep track of possible reactions. So we start in state A. If G2 is enabled, we're going to produce output A2 and transition to state C. If G4 is enabled in the next reaction, we'll produce A4 and transition to D. If G1 is enabled in the next reaction, then we will produce A1 and produce A. Wait a minute. Did I let the refinement react in this transition? I actually did, right? I'm in state D. The refinement reacted, but there's no transition out of D that's enabled, so its reaction was to stutter. It just stayed in the same place. And then the higher level state machine reacted. Okay? Then from A, I might go back to D. Oh, D. I went to D. So is that a history transition or a non-history transition? It's a history transition, right? I went to D. So I remembered where I was. Okay? So now, once I'm in D, if both G3 and G1 are enabled, okay, then my reaction will be to simultaneously produce A1 and A3 and transition to A. Okay? Where will I come into the next entry into B? Into C, right? Because I took the transition from D to C. Right? Yes?
Can you state again why, if there's history, that means there's 4 states in such?
Because think about this transition, right? When I went from D to A, okay, I'm now in state A. If my next transition brings me back to B, where should I go? I need to remember where to go, right? I have to either go to C or D. If it's a history transition, I'm going to go either way, actually, it's going to go to C. But in both of these cases, anytime I go from A to B, if I have a history transition, I have to remember where I left off. So there's more information. Just knowing that you're in A is not enough, right? If the only thing you know is that you're in state A, you're missing a piece of state information. So I'll make this more explicit by actually, the way to answer this question, by the way, always, whenever you've got a composition of state machines and you want to know definitively what does it mean, translate it into a single flat finite state machine. That single flat finite state machine is the definition of the meaning of that composition. Okay, and so that's what we're going to do in just a minute. Yes? Good.
So in this state machine, the G's are the inputs and A's are the outputs. So suppose we represent the hierarchy state machine as a one input, one output model. And when both of them are reacting, the hierarchy part of the B and also the main machine, in that case, what do we actually see on the output board?
Yeah, so that's a good question. I'm assuming here that A1 and A3 are both distinct pure output ports. So there's no possibility for a conflict here, right? But suppose you had a single output port with an int data type, and the transition in the refinement sets the int to 0, and the transition in the higher level state machine sets it to 1. Okay? Then what is the output? It's a single reaction, so the output cannot be both 0 and 1. And it can't be a sequence, 0 to 1. It's a single reaction. It can only have one value in the data type. Okay? So again, you need a semantics. And there are several choices. One choice is it's undefined. Your state machine is erroneous. Reject it. Okay? So that would be one possible answer. Another possible answer, which is actually the default in S/L for integer data types, is the output is the sum of all the values that are produced. That strikes me as a little bit weird, but that's a choice, right? For any data type that can be added, it says, all right, if two transitions assert the same value in the same reaction, add them. Okay? A third possible choice is there actually is a well-defined order to how these assignments are done, because the refinement always reacts before the containing machine. So as a consequence, these assignments to the output do occur in order. You could say Well, the output is going to be the first value, or it's going to be the last value. Those are all choices. Make one of those choices, and you've got a formalism. Fail to make one of those choices, and you don't have a formalism. Okay? I think the choice that's made in the textbook is that it's an error. Okay? But I honestly don't remember. Yes, there was a question in the back. Right.
But the outputs are produced simultaneously.
Right.
So there is a notion, but you have a concept of time fitting in anywhere?
Yeah, so reactions are all instantaneous, and the environment chooses when they occur. Okay? So at a reaction of a state machine, there are input values and there are output values. That's it. No. The transition of the refinement doesn't occur in a distinct reaction from the transition of the containing machine. It occurs in the same reaction. It happens first, but within one refinement. So think of it as, okay, what it's expressing is the decision logic of trying to decide what the values of the outputs should be in this reaction. And it's an imperative logic, okay? So in order to decide what the outputs are going to do, I first consult this guy, see what it asserts about the outputs, and then I consult that guy to see what it asserts about the outputs. And after I've consulted those two in that order, I know what the outputs are. And that's what the outputs are in that reaction. Okay? Yes, Gil. Setting variables. So that's a really tricky one, right? And you have to be careful. And this is where a lot of state machine formalisms don't get it right. Okay? In our formalism, the set actions are distinct from the output actions. Okay? And the set actions are all performed after the reaction has been concluded. Okay? So, for example, if I do a set action here, and I have a guard that depends on that variable up there, the guard will be evaluated with the old value of the variable, not the new. Okay? That turns out to be an important requirement, but for very, very subtle reasons that are a little bit beyond the scope of this course, but we'll hint at them when we look at feedback compositions of state machines, okay? Because it's a way of ensuring deterministic behavior of feedback compositions. But excellent question. Are there any more questions? Yes, Nikunj.
It's a follow-up on my previous question. When we are taking this transition from D to A,
yeah.
and suppose we have flattened the state machine now, in that case, can we not say that G1 is just ignored? Because even if G1 and G3 occur simultaneously.
Okay, let's answer that question by flattening the state machine. So I'm going to do that. So here is a flattened version of this state machine. Okay? And this should also... Sean? Josh. Sean was back there. Yes, thank you. So this will hopefully answer Josh's question, okay? So I initially start in AC. Hopefully that's clear to see, right? And then I could transition to BC, okay? And from BC I could transition to BD, or I could transition back to AC. Okay? If I'm in BD, however, because this is a history transition, it would be incorrect to transition to AC. Because if I go to AC at that point, then next time I enter B, I'm going to enter at C rather than D. Okay? So I have to, if I go to A, I have to remember where I was in the refinement. So AC says I'm in A, and if I enter my refinement again in the future, I should enter at C. And this state says I'm in A, and if I enter my refinement sometime in the future, I should go to D. So that issue of remembering where you need to pick up where you left off has to be captured in the state machine because it is state information. Yes? Sean?
If instead of going from A back to B, there was like a long chain where A went to like other states and then went to short B, when you split it up like down state A, C, and A, E, then that means that in the added states, there would have to be like 2 copies of the both frames that you have like.
Excellent observation. So if I have a whole bunch more states here, right, then the total number of states in my system will be the product of that number of states and the number of states in the refinement. Suppose I have 4 states in the refinement and 4 here, then this thing has exploded to 16 states, right? But if it's 8 and 8, it's exploded to 256 states. As a consequence, you can really express very complicated behaviors very compactly. Right? Yes? Because the representation here, the way to interpret this is I'm in state A, and next time I enter B, I should enter at C. Okay? Remember that state is everything about the past that I need in order to move forward into the future. Okay? That's what it means to have state. Okay, so let's look at a refinement. Suppose that we don't have a history transition, but a reset transition. Then I no longer have to remember where I left off. Okay, so the flattened state machine just has to have a single state representing A. I don't need to remember where I left off. So if I'm in A, if I ever in the future re-enter B, I'm going to re-enter at C. Okay? So reset transitions are a little more compact. Okay, also, a notational convenience, we allow for preemptive transitions, and again, David Harrell introduced these as well. So a preemptive transition is one where if the guard is enabled, we don't allow the refinement to react. Okay? We just preclude that possibility if the guard is enabled. All right? So it would be a good exercise to make sure that you understand the flattened version of this state machine and how the preemptive transition is captured in this flattened version. Okay, but let's apply it. So here's my simplified interrupt controller. I'm just going to say, all right, if my interrupt is inactive, then I'm going to have a preemptive transition. Okay? So when this machine reacts, if assert is true, I will not allow the refinement to react. Okay? I will instead transition to the active state. And when the active state, when that refinement produces an output return, I will transition back to the inactive state using a history transition. Okay? So now this is starting to look like an interrupt, right? And in fact, I can stick in my interrupt code and see that, yeah, actually this is kind of how it behaves, right? And if I make these state machine refinements, I can say, all right, I'm executing main, and I'm wherever I am, okay? If assert occurs, main is not allowed to react. I'm just going to stay where I am, and I'm going to transition into my interrupt service routine, which now no longer needs an idle state. It has an initial state D, okay? Notice that's a reset transition. When I enter the interrupt service routine, I always enter at the initial state. Okay? I execute until I produce the output return, at which point I will transition back to inactive with a history transition and resume where I left off here. Okay? So, we now have a formal model. I can ask a formal question. Is C always reached? It says nothing about speed. It just says that if I look at an infinite history of reactions, there will be an infinite number of times at which, an infinite number of reactions at which active is asserted. Okay? In other words, Actually, I'm not even sure I need that constraint to answer this question, because if I get only a finite number of assertions, I don't think it changes the answer. What this was trying to get at was that I didn't want to examine the special case of where an interrupt request never occurred, or an interrupt request occurred only once. Oh, actually, that is important, because if an interrupt request never occurs, the timer count variable is never going to get changed, and consequently, in fact, I will never reach C, because timer count will never hit 0. Right, so I do need that constraint. Okay, so all it's saying is, the timer hardware didn't fail. It's going to keep requesting interrupts. Okay, that's what that assumption asserts. Okay, so now we have a formal model. We can ask a formal question, and there is one answer. Right? Either C is always reached or C is not always reached. There's no two answers here. It's not subject to human interpretation anymore. So what's the answer? Right. If on every reaction assert is true, then in fact C will never be reached. I want to emphasize this because this wouldn't have occurred to you. If you're writing embedded software, right, and you set a timer to trigger every 2 milliseconds, you kind of think, okay, it's not going to be asserting interrupts all the time, right? But actually, given the way the system is defined, the interrupt request is an input. You don't have control over inputs, right? What if your hardware has a stuck at fault, and in fact your interrupt request line is stuck at true? That's actually, within what the system we've defined, that is a valid situation for the environment because it provides an input assert. It just happens to provide it all the time. Okay? But this could also occur in practice in the C program, right? Suppose that this body of code always takes longer than the time between interrupts, right? Then effectively, assert will always be, well, no, that's not quite true. Suppose that this body of code always takes longer than the time between interrupts, right? So the interrupt service routine actually takes a long time to complete its action, long enough that the timer hardware triggers again, okay? Then it could occur, yeah. Yeah, but to enable them again, right? So that if the timer has pulled that interrupt request line high, it could just hold it high until it gets a reaction. Okay, so even with interrupts being disabled and these things not nested, but I'm glad you raised the question of nesting because if you nest, before I do that, I'll show you what happens if you allow nested interrupts. Okay, but here this hierarchical state machine can be flattened. Okay. And now the flat state machine, I can do exhaustive search. Okay? I can look at all the possible behaviors, and I can find a trace that never gets to C. And that trace is called a counterexample. Okay? It's a demonstration that my assertion that this program would eventually reach C is not true. Okay? The way the program is defined. And that's the kind of analysis that you can do. Yes? If you nest interrupts, if you allow nested interrupts, then you have a harder analysis problem because the state machine now becomes infinite. Okay, and if you think about the way it works in C, in fact, within the logic of C, it is infinite, right? Because every time an interrupt occurs, a bunch of stuff gets pushed on the stack. You go into the interrupt service routine. If nested interrupts are allowed, while you're in that interrupt service routine, if an interrupt occurs, you push a bunch more stuff on the stack. Your stack keeps growing without bound. That's infinite state. Okay? So that analysis problem becomes much more difficult. Yes? Yes. No, because this is a reset transition, and this is a history transition. If they were both history transitions, then the state space would get much bigger. Yes?
And so we can represent this behavior in a normal model as well as a asynchronous like composition model.
Well, this is a normal model. It all depends on what you mean by normal.
Without the hierarchical of composition. But it's just much neater to do it this way. Right?
I'm sure you could come up with even a synchronous composition of state machines that would correctly capture this behavior. But my guess is it would be a much harder to understand model than this one. Yes?
There are some underlying assumptions we have about the search signal that we are assuming that if we didn't do the transition, a search will always be high, rather than a search will only be high for one period.
I know. There's all kinds of assumptions. But I want to emphasize that the formalism sort of circumvents those assumptions about how the hardware works, because this formalism is an abstraction. And all it says is, when the environment chooses to have this machine react, either assert is true or it's not. That's all the formalism says. Now, it's up to you when you design the hardware to try to make the hardware behave like that. Okay?
I mean, in this way, if you're in a state active and then a search is true, you will just ignore a search because there's no
Right.
decision coming out from active.
That's correct. If you're in the active state and you react, and assert is true, there's no transitions in your refinement or in your main machine that are triggered by assert. Therefore, assert will be ignored.
In this way, you will always reach the state C.
No, you don't always reach the state C.
Because if assert only value for one reaction.
Yes, but you have to reach state C in the inactive state, right? So, and this is a preemptive transition, okay? So if you transition from active to inactive, and then in the next reaction assert is true, this machine will not be allowed to react because it's a preemptive transition. Okay, so as a consequence, I will never get to C. Now, by the way, there's other scenarios also that can keep you from getting to C. But the way these formal methods work is you just, you want to prove a property about a program, and if you've found a counterexample, you've shown that that property is not true. Okay? It's not the only counterexample necessarily, but if the property matters to you, it's enough to have one counterexample to say, oh, I got to fix this. Yeah. Josh, did you have a question?
Yeah, what does the dot signify on the transition from inactive to active on the arrow?
It means it's preemptive. So that means that when this machine reacts, if assert is true, the refinement is not allowed to react. And instead, this transition gets taken immediately. That's what a preemptive transition means. Yes? You could, yeah. Yeah. In fact, pretty much all of the notation that we've introduced, you can eliminate and do everything with flat state machines. You don't need default transitions. You just need states, guards, and transitions, and that's enough. The problem is interesting state machines get really big. So, but if you're a computer program, you don't care, right? Up to a point. And so, actually, the way that a formal analysis tool would work on a state machine like this would be to first construct the flat, completely described state machine in a simpler notation, and then apply algorithms to that. Okay. All right. Let's let me close this discussion, and then I really want time to talk about the projects, but just I wanted to give you a little snippet from of the notation that Harel introduced in 87. So this is one of a Harel-style state machine, and it has, at the top level, two states, on and standby. Okay? In the on state, there are two sub-state machines, which Harel declared to be synchronous composition of two state machines, except he didn't get it quite right, but it was close. Okay? But, fixed up, it's synchronous composition of two state machines. Okay? So he called that an AND state. So this on state is an AND state because when you're in on, you're in normal and mute. Okay? Right. And, and then, well, the rest of it is, I think, hopefully pretty clear. Okay, I think I've said all this. We're going to talk a little bit more about the algorithmic techniques that we use about this when we start getting into the analysis. Okay, I'd like to turn to talking about projects. And so, project overview. You should form teams of 3 to 4 people. In the past, it's always worked to have you self-organize. Okay, but if that fails, appeal to us. You could talk to your GSI first. I would recommend using Piazza also. Okay. The effectiveness of your project will depend on an effective technical plan with realistic timelines. You've only got till the end of the semester. Okay. If you decide you need to order a bunch of parts from China, they may not get here in time. Okay? And if they come in January, it's too late. So you need to be realistic. Okay? We're going to strongly encourage using hardware that we've already got on hand. We've got a whole bunch of stuff, and I'll tell you a little bit about what that is. But we don't want to rule out projects that actually need some stuff that is purchased separately, and we have a modest budget that we can use to spend on these projects. Okay? So nominally, each team can spend up to $200 or so without us worrying about it. Okay? More than that is not impossible, but, you should talk to us, and there better be a good reason. Okay? All right. So it's very important in these projects to have an effective use of models. You've got to use the concepts of the course. If you just hack together a cool demo, you're not going to get a very good grade. Okay? In fact, it is neither necessary nor sufficient to have a cool demo to get a good grade. You could have an extremely boring demo with just a beautiful analysis of what's going on. And that'll be an ace project. Okay? You need to have a good software architecture. All right? And don't just hack something together. It's not enough that it works. Okay? It should be modular. It should be, using the principles of model-based design and platform-based design. You should choose your hardware well. First criterion is, do we have it on hand? Okay. Second criterion is, will it do the job? I guess maybe it should be the other way around, right? Because if it won't do the job, then it doesn't matter whether we have it on hand or not. Okay. All right, I think I've said all that. Now, in terms of particular hardware, so one of the things that we'd like to encourage projects to do is work with a technology that's fairly recent, but is really kind of progressed rather rapidly, which is individually addressable LED displays. And I'd like to give you a sense of why that might be an interesting thing to do. So first of all, there's a huge wealth of possible projects that you could do with this. And so I'm envisioning things like, interactive holiday decorations, right? A Christmas tree that lights up when you come close to it, or that reacts nicely when you wave your hands, or, but there's other, in fact, if you go to the project website, there's a pointer to a really nice YouTube video of a cube of LEDs that reacts. You can wave your hand at it, and a wave of light propagates through this cube, okay? But we want you to be kind of inventive, right? But it should be interactive, so you need some sensors. But there's something really interesting about these LED strips. And by the way, I wasn't joking when I talked about ordering stuff from China. We ordered 100 meters of these LED strips from China, and they're stuck in customs. And they have been for a while. And the vendor, promised 1 week delivery, but it's been several weeks. And so it's a little bit of a problem, right? Ordering lag times are very unpredictable, and they can be a huge risk factor in your project. You have to take them into account in your planning, okay? But anyway, we expect, hopefully within the next week or so, to have 100 meters of these things. Now, it's a big 100-meter roll, and it turns out you can take your pair of scissors and cut it anywhere, okay? And there's 3 wires, okay? One of those wires you don't want to hook up to your microprocessor because it's the one that provides the power to all the LEDs. If you try to power all these LEDs with your GPIO pin on your microprocessor, you will fry it immediately, okay? And that will eat up a good chunk of your budget and some of your time, right? So you provide power to them, and then you provide a single digital line and a ground. Okay, I can cut this thing anywhere, and I've got a single digital line. How do you suppose I tell the third LED to be red and the fourth LED to be blue? Any ideas? Sorry? Yeah, so one possibility would be that each of these LEDs has an address, okay? And you can somehow, using a serial line, pump that address into this one wire, right? And that LED that has that address will react, and you can set the color. But actually, that's not probably a very good solution because you can cut this thing anywhere. So how do you know which is the first LED, which is the second LED? How does the first LED know it's the first LED? Right? Yeah? Other ideas? The signal strength might decrease as you go down the line. Yeah, but that would be an analog technology, which is going to be a lot more iffy than a digital technology. Yes? Bunch of shift registers. Yeah, but actually it doesn't quite work that way. But I'll give you just a little quote from the website from Adafruit, which sells a bunch of these. Okay, it says the protocol that's used is very timing specific and can only be controlled with microcontrollers with highly repeatable 100 nanosecond timing precision. We have example code using the Arduino Uno or Mega microcontroller at 8 megahertz and 16 megahertz, but it will not work with Raspberry Pi, Basic Stamp, NetDuino, or any interpreted virtual machine microprocessor or any processor slower than 8 megahertz. You cannot drive these things from a Linux box. Even this one. You can't get the timing precision. Okay? In fact, the whole way that these LEDs work is if you pause for long enough on this digital line, then your next signal, the first LED, will react to it. Okay? And then once it has reacted to it, any subsequent signals that come within a certain amount of time will be passed on to the second LED. And it will react to that, and so forth. So you've got to very precisely control the timing in order to write to these LEDs. There's a few variants of these strips. You can get them in grids or in rings. So, but we want you to consider projects that connect them up with sensors. It's not going to be enough to just make a display, right? It's got to be some kind of closed-loop behavior. We've got a partnership with the Invention Lab, which has a bunch of sensors you can use, okay? And even, we may, because of the size of this group, we may really stress the Invention Lab resources. Generally, the way these things work is you borrow them, and you can return them unless you destroy them, in which case we pay for them. But that counts towards your $200 budget, okay? We may have to order some if your projects require more of some particular sensor than what we've got in the Invention Lab. So take that into account. There might be an ordering lag. But the kinds of sensors are things like flex sensors, right? So you could make a wearable strip, a necklace that, reacts to bending in your arms or whatever, okay? Those are possibilities. We have moisture sensors, so you could make a version that, changes color if you start to sweat when you're working on the treadmill. I don't know. There's a whole variety of different sensors, but if you go to the project website, you can find these. We also have, in the Invention Lab, there's some actuators, and we also have a bunch of actuators in the Cori 205 lab. In particular, these are kind of low-level servos, so motors you can drive, okay, using PWM output. These are particularly interesting. These are bioloid devices. So that little machine there is driven with a serial port connection, and you can use it to build up, various axes of control from a motor. Processors. There's a variety of possibilities here, okay? And we're open to projects using processor boards that we don't have or that are not on the list, but we strongly discourage it. One, lead time is a problem. You have to order it. Two, there's not going to be anyone around you with debugging expertise with these who has figured out how to get the software to work. You're going to be on your own on that, right? So this semester, we're going to be steering people fairly strongly towards using this particular board, okay? It's an mbed processor made by Freescale. It's got a 3-axis accelerometer on it and a variety of other sensors. I forget exactly what, all right? It's not a very fast processor. Compared to the Beagle board, this is a 1 gigahertz ARM Cortex A3, this is pretty much the same processor that's probably in your cell phone, okay? This is not, all right? And this thing comes with an image of Linux that you boot up. If you write a program under this image of Linux, it will fail to drive those LED lights, okay? You're going to have to use the bootloader and write raw code if you use that, and that's probably not a good choice, okay? This guy, on the other hand, you're going to be writing low-level code. But this is a 32-bit microprocessor as opposed to an 8-bit microprocessor, so it's a little bit more beefy and faster than the 8 megahertz or 16 megahertz Arduino processors. Okay, I'm almost out of time, but I have a couple of other high-level points that I really want to make. Google is your friend, okay? If you don't use Google and you're doing stuff with this kind of technology, you're crazy. I mean, you're not going to get anything done, all right? But you must attribute your sources, okay? It is cheating to download open source code and not tell where you got it, okay? So building off the work of others is okay. In fact, you have to, right? There's no way to do something interesting without building off the work of others. But failing to credit the others is not okay, all right? You should bend over backwards to credit your sources, which could be your colleagues in the class, by the way, okay? A professional always knows his or her sources. And by the way, if you go for a job interview, instead of saying, oh, I used an Arduino, knowing something about what an Arduino is important. So here's a couple of examples. So, all right, we're using the Arduino library for the NeoPixel, that's these individually addressable LEDs, provided by Adafruit, which is written by Phil Burgess. By the way, that's not always easy information to find, okay? But everything you use was created by a human. Who is that human? Or those humans, right? And it's distributed with an LGPL license. Pay attention to the licenses, right? You should know what the license is of any software you use. In the case of Arduino, you could get really carried away. So we used an Arduino Mega made by an Italian company, Smart Projects. The Mega is part of the Arduino family of open source software and hardware that started in 2005 as a project for students at the Interaction Design Institute in Ivrea, Italy. Arduino is named after a bar in Ivrea, which in turn is named after an 11th century Italian king. Trust me, if you say that in a job interview, they will be impressed. You know what you're working with, right? All right. You have to turn in a project charter, okay? And we've put on the website a sample project charter to give you an idea of what we're expecting. All right? So I encourage you to look at it. So this is a somewhat tongue-in-cheek project that we've entitled Proper Respect. And the goal of the project is to create a figure, like a stuffed animal or something, that you will place in a professor's office, maybe a little golden bear, okay, that will bow to the professor when the professor walks into the office. Okay? That's the goal of the project. All right? The project approach, this is really important, okay? You want to model the arrival and presence of the professor as a state machine governed by a combination of sensor inputs, focusing on the timing of entry and the control of the robotic actuator. The goal will be to accurately detect arrival through the doorway and to time the reaction of the robot for maximum effect. Okay? So arrival through the doorway is not the same as just there's something in front of me. How do you model that? Right? How do you detect the difference between arrival at the doorway and the professor opening the door for a visitor who's coming in? Okay? These are questions that you can start to answer by trying to construct a model of this system. Okay? You should have some idea of what resources you're going to use. Are going to use the embed processor from Freescale as the processor core, driving servos. You can leave some ambiguity. You're not sure whether the bioloids will be more convenient or the servos that are in the invention lab. You can leave some flexibility there because you want to be able to explore and so forth. Okay? So take a look at the project one. A final word, teamwork. Teamwork is really important here. And teamwork sometimes fails to work as well as one would like. Sorry, we're all human. It's really important, though, to respect your team members. It's one of the reasons we've asked graduate students to obey the undergrad drop date, which means that if you haven't dropped the class, we expect you not to drop the class. Okay? If you do drop the class, it should only be with the concurrence of all of your team members who are also dropping the class. Okay? Otherwise, it's just not acceptable. All right? The other thing is we're also asking you to do a peer evaluation of your partners on the first sequence of labs, okay, because that's sort of a trial run on working as teams. And in my experience, these peer evaluations have almost always been perfectly consistent. They allow you to self-evaluate how much did I contribute to the project and to evaluate your team members, and I've rarely found a discrepancy. The people who slacked off said they slacked off.